This video is going to review how to draw Lewis structures and perspective diagrams for that Lewis structure. I'm going to use for an example XE F4 xenon F4. So the very first thing you have to do is count the number of electrons in the structure. The atoms are connected to their outer shell electrons, so we only include outer shell electrons in a Lewis structure. So let's look at xenon. It's in group A of the periodic table, so it has 8 outer shell electrons. There's 4 fluorines. Each one has 7, so there's 4 of them, that's 28. Now, if this were an ion, this happens to be a neutral molecule. If it were a negative ion, that means it has an extra electron. So for every negative charge, if it had it, we would have to add another electron. Conversely, if this was a positive ion, we would have to subtract 1 electron for each positive charge from this total. Now, this is a neutral molecule, so in fact, all we have to do is add these up and get 36. Now that we have 36 electrons, let's draw the Lewis structure. And we'll first of all put the xenon in the middle and the fluorines around it, which makes sense. It's a fairly symmetric structure. We've already got 8 electrons in here because each bond is 2 electrons. But now let's put lone pairs in. And I think it'd be obvious that fluorine, we want to fill out the octet. So we're going to put 3 lone pairs on each of the fluorines to produce this structure. But remember, we need 36 electrons in here. How many electrons do we have here? Well, in terms of the lone pairs around fluorine, each one has 3. So there's 4 of them, that's 12 lone pairs, and 2 electrons per lone pair, that's 24. And then the bonds count 2, so that would be 26, 28, 30, 32. So this structure only has 32 electrons. So we have to add 2 pairs, either in a bond or essentially as lone pairs. Now the fact of the matter is we can't add any more electrons to the fluorine because it has an octet. Fluorine is inferior to the periodic table. If it were further down, like phosphorus and sulfur, we could expand the octet. So we're going to put them as lone pairs around the xenon. And we don't put them directly on line with the bond, because that would be confusing. These are non-bonded, so we put them between bonds. And so this would be our sketchy diagram, our first Lewis structure that doesn't really show the geometry. Now, the next thing we have to do is determine the formal charges on the atoms, because in a Lewis structure, you want to minimize formal charges if you can by not violating the octet rules. So let's look at it. This is the structure we came up with. Let's look at the formal charge on the fluorine. Now remember, in determining the formal charge, you assign electrons to an atom and compare it to the number of electrons an isolated atom would have of that element. So here's fluorine. The lone pairs we assign completely to the F. The bonded pairs, it's logical just to assign 1 electron to each atom in the bond. That means we assign 7 electrons to the fluorine. While atomic fluorine has 7 electrons in the outer shell, so its formal charge is 0. If it were to have 8 electrons, that means it would have 1 extra electron, so it would have an extra negative charge. We'd have to essentially have a negative charge, not a positive charge. Likewise, if we had only 6 electrons assigned to this, instead of 7 that it's supposed to have when it's an atom, that means it's deficient in electrons. So it's going to have 1 fewer electrons than protons, so it's going to have 1 positive charge. The xenon, we can do the same thing for, too. So we have 4 bonds, that's 4 electrons contributed to the xenon in terms of assigning for formal charge, and the 2 lone pairs contribute 8. Xenon is in group 8, so it likewise has a formal charge of 0. Now, given this Lewis structure, we have to turn that into a perspective diagram. How do we do it? Well, the first thing we have to do is look at the central atom and ask the question, how many electron clouds are coming out of the xenon? Well, there's 1 for each bond, but then, the lone pair is 2 electrons too. That means there's 1, 2, 3, 4, 5, 6 clouds coming out. So then what we do is go look at a template, a perspective template for the various geometries. If you have 3 clouds coming out of a central atom, and a double bond would count as 1 cloud or a triple bond, that would be trigonoplanar. 4 clouds coming out is a tetrahedron. We've seen that before. Let's skip to the octahedron. That's when we have 6 clouds coming out. So this obviously has 6 clouds. That means we have to use this template in drawing the perspective diagram. So here's the perspective diagram. I've just copied it and placed it down here. I should have put the xenon atom in there. The question is, where are we going to put the 4 fluorines and the lone pairs? For an octahedral geometry, lone pairs we talked about go into the axial directions. They don't go into the equatorial plane. So we assign the 4 fluorines. We put a fluorine at the end of each one of these bonds and the lone pairs in the axial positions up and down. So that means our electronic geometry is equatorial. Octahedral. It's octahedral. So now what is the molecular geometry? Well, we're just going to copy this and place it over here and simply leave the geometry of the clouds the same, but remove the lone pairs. Because all we're interested in is the geometry of the molecule without the lone pairs. And if we do so, you see these are all lying in a plane. And remember, this is xenon in the middle. So this is not a tetrahedron as many would suspect, because I have 4 clouds coming out, because the geometry was set in the first step by figuring out the geometry of the 6 electron clouds. This, in fact, is a square plane. It comprises just the square equatorial plane of the octahedron without the lone pairs. So this is what you have to do. Literally count the lone pairs coming out of the central atom, select the perspective template that has the same number, and then simply position the atoms and the lone pairs in the right position.